Hi, my name is Anthony Gilchrist, and today I'm going to be talking about the research I did for my dissertation at the University of Southampton for my master's degree in maritime archaeology. So, when I was looking for our ideas for my dissertation last winter, of course I was in England, so I was locked down in my dorm room. One of the many toys I found were low-cost ROV systems. They have proven especially useful to archaeologists in recent years. Some of the uses they've had for them have been basic exploration and photogrammetry. Some examples are on the screen, such as the blue ROV2 on the left and the open ROV on the right. There's also the Chasing M2 and the Fish V6. When we were trying to find, when I was looking at the uses for it, photogrammetry was a big one that popped out at me. The main problem was they weren't able to create 3D models of shipwrecks completely remotely. This being because a scale bar needs to be placed on the wreck or the object you're surveying to physically scale the model. And normally you can't do that with these low-cost ROVs because they don't come with a manipulator arm. And if they do, you have to spend thousands of dollars extra to get a manipulator arm. So most of the ones surveys I found all use divers too to put down some sort of grid system or something to scale their models off of. And I wanted to eliminate this. So my advisor Felix Pedrotti recommended that I try scaling using stereo cameras. And the models would be scaled using the distance between the lenses of two cameras. So I reached out to Agisoft support, and they wrote me a Python code that could scale based off of the distance between each set of image pairs from a set of stereo cameras based off of the distance between cameras. So the research questions for this project were, can a low-cost ROV system be used to accurately record underwater archaeological sites without the use of divers, which is the reason we went with the stereo system, and which leads into the next question is, can stereo cameras be used to scale 3D models terrestrially and underwater? And then basically what were the benefits and pitfalls of using a low-cost ROV system? So to capture the stereo images for this survey, we used dual GoPro cameras on the majority of the models. One of the models used a DSLR camera, and one of the models used a single GoPro camera. The GoPro cameras, to get them to be lined up to make a stereo pair, I used a flash bracket I found on Amazon along with some other miscellaneous parts to get everything to connect. The main problem with the flash bracket was that the cameras like to sway just due to the nature of how the action camera mounts go together. To solve that problem, I went and got screws from the local hardware store that I could torque using a drill, and that seemed to solve the problem. The problem didn't seem to be as prevalent in the actual connection from the flash bracket to the ROV. The ROV itself is a Fish V6, and I really like this ROV because it's omnidirectional, so it can go in basically any conceivable direction underwater. It's controlled by a tablet plugged into a remote controller, which is then plugged into a 100-meter tether that's on a spool that plugs into the back of the ROV. The ROV is powered by an onboard battery that lasts 3 to 4 hours. So you have to physically take the ROV out of the water and charge it when it's out of battery, which is a disadvantage of the Fish V6. What I should say about the stereo cameras is to capture the images with them, they had to be synchronized manually, meaning that I had to press the shutter buttons at the same time. The mode they were on was time-lapse at taking an image every half second, and I managed to synchronize them well enough that I get the same amount of images out of each camera, so it worked reasonably well, and it didn't seem to affect the overall outcome. So to actually process the images, the file names need to be correctly inputted into the program, and the proper file naming format is at the top of this slide. It's right lowercase, or lowercase right underscore whichever number the image pair is, and then the corresponding image would be left or lowercase left underscore whatever the corresponding number is. And this file renaming the files like this turned out to be really easy on Mac and not so easy on PC, because PC likes to add brackets when you rename files. So to get rid of these brackets, we had to enter in a script onto the Windows computer to actually get rid of them. And this script was finicky at best, but it did end up working. The actual Python script is relatively easy to put in Agisoft Metashape. All you do is go to the top and click Run Script, and then select your Python file off of your computer. The only thing you really would need to edit on the Python script would be the scale bar distance, which is at the bottom of the script, and that is in meters. So the example I have up has it at 25 centimeters or 0.25 meters. If you wanted to change that, you wanted to do 35 centimeters, you'd put 0.35, or if you wanted to do 1 meter, you just write 1. And to do that, you would want to use a Python code editor. You don't want to use a regular text editor, because it won't work. It will make the code all funky. So to first test the viability of scaling using stereo cameras, we chose a terrestrial site, because if it wasn't going to work terrestrially, it most likely wasn't going to work underwater. The site we chose as our terrestrial site is the CMA Hulk, which is located on the Center for Maritime Archaeology's campus in Southampton, UK. The images were all taken by my advisor, Felix Pedrotti, with a DSLR camera and stereo GoPro Hero 9 cameras. 3 models remained, one with the single DSLR camera, scaled using a 1 meter scale bar, and the other 2 were taken using the stereo GoPro Hero 9s, one with the cameras spaced 25 centimeters apart, and one with the cameras placed 35 centimeters apart. The model made with the single DSLR camera that was scaled with the 1 meter scale bar that can be seen on the bottom of the top right picture ended up with a 1.5 meter scale bar accuracy. The model, which was made with the cameras placed 25 centimeters apart, ended up with 210 scale bars that gave it an average scale accuracy of 0.0017 meters, which is much better than 1.5 meters. Then the 35 centimeter model ended up with the same average error, so it showed when we changed the baseline, it didn't actually affect the accuracy of the scaling, which is good to know for if you're trying to streamline something underwater, or if you have more room trying to use this method terrestrially, you can have a bigger scale bar. And when we put these models into Cloud Compare, I saw no real differences. So it really did prove that this method is a viable way of scaling models to a very high degree of accuracy, and required relatively little effort aside from getting the Python codes to work. So to test this method underwater, now that we had proved it terrestrially, we decided to go find an easy site that I could learn to pilot the ROV at, and could find an object to 3D model, and would also be relatively easy to access diving. So I chose some rocks off of my family's dock on Lake Winnipesaukee in New Hampshire. Here I created 2 models. I also learned how to pilot the ROV in a flight pattern which would be conducive to making a good 3D model. The first model I made was diving with a single GoPro, and I scaled that using measurements I took with a physical tape measure, and that resulted in an average error for the scale bars of 0.09 meters or 9 centimeters. I then sent down the ROV equipped with the stereo cameras and created a model that had 266 scale bars, which resulted in an average scale bar error of 0.0015 meters, or less than a centimeter. So it was a lot more accurate than the single camera model, and just the model I made using the ROV beat the accuracy that I got scuba diving. So to test this method on a real archaeological site, we went out to a steamboat that is located in Lake Winnipesaukee, not too far from the rocks that we made 3D models of. This steamboat, not much is known about it. It's in about 20 feet of water. It's around 20 feet long. It took me multiple tries to actually collect the data for this. It turned out to be more complicated finding a shipwreck in the middle of the lake than it is to find rocks off of a dock. This ended, and this is where I think that low-cost ROV systems could definitely use some improvement, is on the positioning system. But after multiple tries, I managed to create this model without the use of a diver and solely using the stereo cameras on my ROV system. I ended up with 417 scale bars and an average error of 0.11 meters, which I'm attributing to just trying to orient the ROV, going a little too fast in some of the tries. It was a much bigger object in the rocks, and therefore used a lot more images. And then to show the usefulness of the models I created, I made some site plans using Adobe Illustrator, and I really think that sort of shows the final product you can get from it and how well we can record a site. Because as you can see on the bottom left corner, the shipwreck itself is quite murky, and just from one picture you can't see the whole wreck. Whereas now we have a complete model of the wreck, you know what's down there, and it's a shareable thing. We can share it online. I'm also looking to do some 3D printing or try to 3D print this model, and perhaps make more models of shipwrecks in Winnipesaukee and share the 3D prints around the Winnipesaukee community. So in conclusion, I would still prefer to scuba dive to create 3D models and collect photogrammetry data. This being mainly because the positioning systems on these low-cost ROV systems are still not the greatest, and a diver who has reasonable buoyancy and knows what they're doing should be able to maneuver themselves around an object that you're trying to model a lot easier than you're going to have one of these ROVs doing it. That being said, for certain applications, this ROV system could be, or this sort of system could be great, especially if it's too dangerous to send a diver down and it's something the ROV can go down and do. I would really like to try out this method more, just diving and carrying the stereo cameras, because we know that with the stereo cameras we can scale these models incredibly accurately and much better than any method I currently, or at least any low-cost method I can currently think of for scaling shipwrecks. And this could also be used terrestrially if you want to get something scaled to a high degree of accuracy, have a lot of scale bars, and don't want to manually input 200 scale bars or use an expensive GPS system. The main limitations of this system are, as I've stated earlier, the camera rig likes to sway. Looking at 3D printing a solution to that a camera rig where the cameras will be stationary and aren't subject to that issue, but that's in the making still. The Python codes are still finicky. They're gonna need to be updated at some point by Agisoft, and that's just the nature of how these programs work. They work a lot better than I expected them to, so that's very promising, and Agisoft support has been nothing but excellent in this entire project, so I'm sure they would help update the code if anyone was looking to use it in the future. And mainly with the ROV, the limitation just is that positioning system. They don't have GPS, so it's hard to find objects. They almost need to be diver assisted, but in the worst case scenario, you can use it without a diver and make a scaled model. In the future, I would really like to see other people trying out at least this scaling method, and I'd be happy to share my dissertation or any ideas, and I'm going to place my email on the next slide, so if anyone needs it, they can reach out and get in contact with me. So thank you very much for listening, and I hope you have a great day.